Greetings and welcome to part 6 of the calculus series, and in this video we'll be looking at another application of derivatives on the topic of rates of change. The success criteria for today would be for students to be able to apply differentiation to solve problems involving connected rates of change. Let's recap what we've learned so far. We started on the concept of the derivative, that for any given function at any given point, the derivative tells us the gradient of the tangent at that point. We can also call the derivative the gradient function. We have also learned that for power functions, the derivative of ax to the power of n is anx to the power of n minus 1. In the last video, we looked at an application of the derivative to help us find the equation of the normal. In this video, we'll be looking at a different perspective of the derivative and to think of it as a rate of change. We want to understand how fast a quantity like y is changing with respect to time. Aside from the power rule that applies solely to power functions, we've also come across a few general rules. In part 1, we've covered the sum and difference rules. In part 2, we learned the chain rule. In part 3, we studied the product rule. And in part 4, we transformed the product rule into the quotient rule. If we focus on the chain rule, just by substituting the letters, we can rewrite the chain rule this way. This version of the chain rule connects dy dt, the rate of change of y with respect to time, as the product of dy dx and dx dt, which is the rate of change of x with respect to time. This version of the chain rule is commonly referred to as a connected rates of change. A geometrical intuition of this formula is as follows. If we rearrange the formula this way, you can see that dy dx, which is the gradient function, is equals to the ratio of the rate of rise against the rate of run. If we draw this on the xy axis and we consider the gradient function at this yellow point, you can imagine that the dy dx, the gradient, is equal to how fast this point is running upwards divided by how fast the point is running forwards. Now let's take a look at an O-level problem inspired by Boyle's law. When a weather balloon is subject to different pressures, the pressure and the volume of the air in the balloon are related by the formula P times V equals to K, where K is a constant. Given that when P is equals to 1.2 and V equals to 2, find the rate at which V is changing with respect to P when V equals to 2. Pause the video here and give this question a good try. Firstly, the graph will look something like this. We have a reciprocal relationship between pressure and volume. As one increases, the other will decrease. Since we are told that P is 1.2 and V is 2, we can work out the constant K to be 1.2 times 2, which is 2.4. This question is asking us for the rate of change of V with respect to P. So the rate of change need not always be with respect to time. In this case, we want it with respect to pressure, so we are looking for dV dP. Since we have an equation connecting volume and pressure, we can go ahead and differentiate that equation. 2.4 over P when we differentiate that. So firstly, we can bring P up to the numerator. So we're going to differentiate 2.4 P to the power of negative 1. So when we apply the power rule, we're going to get negative 2.4 over P squared. Now, if we sub in P equals to 1.2, we're going to get a rate of change of negative 1 2/3 liter per atmospheric pressure. And this matches the diagram because we know that the rate of change has to be negative since they have an inverse relationship. Moving on to problem 2, we have a particle that moves along a curve given by the equation y equals to 2 minus 1 over x squared in such a way that the y coordinate of this particle is increasing at a constant rate of 0.03 units per second. We want to find the y-coordinate of this particle at the instant where the x-coordinate of the particle is increasing at 0.12 units per second. Pause the video here and give this question a good try. Looking at this question, we are given two things. The rate of change of y, or the dy dt, is 0.03, and we have the rate of change of x, which is dx dt, is 0.12. So for illustration, the graph is going to look something like this, and our aim is to find this unknown yellow point. What we can do is we can work out the general gradient using the gradient function. So by differentiating y, we'll get dy dx equals to 2 over x cubed. And while we usually know gradient to be the rise over the run, it is also equal to the rate of rise over the rate of run. So it's the dy dt over the dx dt. So let's sub in those values that we have worked out. We can simplify that to be 1/4. So 2 over x cubed equals to 1/4 tells us that x cubed must be 8, or x is equals to 2. And we can plug x equals to 2 back into the equation that we are given, y equals to 2 minus 1 over x squared, to find y. So this will tell us that this coordinate is 2, 1 and 3/4. So the y value will be 1 and 3/4. Problem number 3. A spherical balloon is inflated with gas at a constant rate of 500 cm3 per second. This balloon begins empty. Find the rate at which the radius is increasing after 1 minute. Pause the video here and give this question a good try. So in this question, we are told the rate of change of the volume, the dV dt, is 500 cm3 per second. And our aim in this question is to find the rate of change of radius, or the dr dt. So we can first apply the chain rule to connect the two rates of change using the formula dv dt equals to dv dr times dr dt. Now let's plug in the dv dt. But in order to find the dr dt, we'll need to know what is dv dr. Fortunately, we are told that it's spherical. Since it's spherical, the volume of a sphere applies. So V equals to 4/3 pi r cubed. And we can differentiate this formula with respect to r to find dV dr to be 4 pi r squared. And surprise, surprise, we got the formula for surface area of a sphere, but we're going to save this coincidence for a later episode. Now, we are still stuck here because we do not know what r is. So we still have to work out what is r in order to find the dV dr. Luckily, we know the rate of change of the volume, so we can find the volume of the balloon after 1 minute, and this will allow us to find the radius after 1 minute as well. So in 1 minute, the volume is going to be 500 cm3 per second times 60 seconds. So that will give us a volume of 30,000 cm3. Now we can apply the volume of a sphere formula again, and this time we'll make r the subject. And this will tell us that the radius is going to be the cube root of 22,500 over pi. So now we can go back to the chain rule, and this time we'll plug in dV dr to be 4 pi r squared with the r that we've just calculated. So making dr dt the subject, we'll get 500 over 4 pi 19.276 squared. That's the calculation for the radius. We just have to press the calculator again, and we'll get 0.107 cm per second. So for these types of questions, don't forget to put the correct units. Now let's go back to this question one more time. But in this variation, instead of finding the rate of change of the radius, are you able to find the rate at which the surface area is increasing after 1 minute? Pause the video here and give this question a good try. Now, if we look at the previous chain rule, we know we can't apply this because now we want to find the rate of increase in surface area, not radius. So perhaps we can just swap the radius for area. We'll get this new chain rule, but it introduces a new problem. We do not know how volume is connected to surface area. How do we find the dV/dA unless we have an equation in V in terms of A? So I'm going to show you two approaches. Method 1 is simply we'll just apply the chain rule again, but in this case we're going to use dV/dr equals to dV/dA times dA/dr. And we know the surface area formula, A is equals to 4 pi r squared. We can find dA/dr, and we already know dV/dr, so this approaches allows us to find dV/dA. But I'm not going to go through this method in detail. Instead, I want to focus on this second method, and that is to consider the product of dV/dr times dA/dt. It turns out that we can swap the numerators. The limit will still hold, and we get a new version of the chain rule, and this is the method I wish to go through. So first we can plonk in the rate of change of volume, the dV/dt. It's still 500 cm3 per second. Next, same as in problem 3, we know the dV/dr from the volume of sphere equation, so we can compute that to be 4 pi r squared. But for this question, we know the surface area equation of a sphere. It's 4 pi r squared, so we can also compute the dA/dr to be 8 pi r. The radius is still the same as what we found in question 3, so we can sub in 19.276 inside. And by making dA/dt the subject, we can compute that to be 51.9 cm squared per second. Problem 4. A conical container with radius 2 meters and a height of 4 meters is initially filled to the brim with water as shown in the diagram below. Water leaks out from the container at a constant rate of 0.18 pi meter cubed per hour. Find the rate at which the height is changing when the height is 3 meters. Pause the video here and give this question a good try. Okay, so let's assume that after a while the water has leaked out a bit, and now the height is some arbitrary value, let's call it h. And the corresponding radius will be r. Using the concept of similar figures, we can find the ratio of the radius to the height. So r over h will still remain unchanged. It is 2 over 4. And we can simplify and find r in terms of h. So r is equals to half h. Next, we turn to the volume of a cone equation. So volume is equals to 1/3 base area, which is pi r squared, times the height h. We can sub in r equals to half h and get the volume in terms of the height. So it will be 1 over 12 pi h cubed. This we can differentiate with respect to h, and this will give us dV/dh is 1/4 pi h squared. The height in question is 3 meters, so when we sub in h equals to 3, we'll get 9 pi over 4. Now, if we go back to the chain rule, we can connect the rates of change. So dV/dt, the rates of change of volume, is equals to dV/dh times dH/dt, the rates of change of height that we want to find. So we can find dV/dt. That's been given to us as 0.18 pi. So let's sub that in. But don't forget, we have to include a minus sign here because water is leaking out. So the height and the volume are both decreasing. Now we can also sub in dV/dh is 9 pi over 4. And all that remains is to evaluate dH/dt. So making dH/dt the subject, it will just be negative 0.18 pi divided by 9 pi over 4. That will give us negative 0.08 meters per hour. And that's our final answer. So before we end, let's turn back to the success criteria that we've set out at the start of the lesson. Are you now able to apply differentiation to solve problems involving connected rates of change? If you have any questions about today's lesson, please post your questions and comments in the comment section below. With that, we have come to the end of part 6. Stay tuned to part 7, where we'll be looking at increasing and decreasing functions. Thank you and have a great day of learning.